Well, welcome back to another episode of Parker's Pensies. This is a podcast where we explore thoughts in philosophy, theology, nature, and life. I love thinking about cool stuff, so come think with me. Today, I'm going to be stretched to the limit because we're talking black holes. So this will be maybe the nature or life aspect of, we'll get into some philosophy, probably some theology too, but today I'm joined with Dr. Sean Ressler. He is an astrophysicist. He got his PhD from Berkeley. Now, currently, he's at UC Santa Barbara in a research position. And his area of expertise is black hole accretion. And so we're going to figure out what the heck that means. We're going to get into all sorts of nitty gritty stuff. I'm super pumped for it. I'm ready to look like a fool. Got to be a fool before you can be wise. So ready to do that right now. Dr. Sean, thanks for coming on, man.
Oh, no problem. It's great to be here. Thank you for having me.
Yeah, I'm really excited about this one because, well, as we talked about off screen, usually I write like an outline for my guests. I can kind of get a grip on their work. And you sent me some videos and I just couldn't even get it. So I'm excited to just jump in right here with you. First things first, well, let's go with what is a black hole?
So a black hole, so I have given public talks before where I say this, I make this statement at the beginning that black holes are the most boring thing in the universe.
Okay.
So they only have two properties. Like two things describe a black hole and that's it. So every black hole, so with these two, so the properties are mass and spin.
Okay.
So like once you know the mass and the spin of the black hole, where spin is how fast it's rotating, then you know everything about the black hole. And every black hole with the same mass and the same spin are exactly the same.
Interesting.
There's a sense in which they're the simplest and most boring objects in the universe.
Yeah. Well,
it's really what is around them that's the really cool thing.
Okay. Well, I've heard someone say that there was charge. Is there charge to a black hole?
That is true. Black holes do technically, or they can technically have charge, but in reality, they never do. Because you can imagine if there was just something sitting there with this massive amount of positive charge, all it would do is attract a bunch of negative charge.
Okay.
And the negative charge would fall in, and then it would eventually.
Oh.
So literally, that is never considered in any of these models. Like people do like hardcore general relativistic calculations where general relativity is Einstein's theory of gravity, which describes what really black holes are.
Yeah.
So I should describe what black holes are more than just they have mass and spin. So a black hole is basically it's a point. It's infinitely dense, zero size point of mass, and it could be any amount of mass, but it's infinitely dense. And this happens when there's so much gravity in an object that any outward force cannot support the weight. So eventually gravity just wins over everything and it collapses into this point. And this point is infinitely dense. And there's a radius so the black hole itself is technically infinitely small, but the mass that it has determines what's called the event horizon radius.
Mm-hmm.
So the event horizon is the point at which even light itself cannot escape, which sounds strange at first because you don't usually think of light as being affected by gravity, but it is. And so light cannot escape from the gravity at this radius, so it's called the event horizon, and that gives the black hole an effective size. And just from the mass of the black hole and the spin, you can determine what this size is.
Okay, and that's again, like you said, that's not by like measuring the black hole itself, but by looking at the event horizon and all the stuff happening on the outside of the black hole.
So everything within the event horizon we can never know about.
Yeah. And that's where you get into your specialty of black hole accretion and like the fluid dynamics and the models of is that right?
Yeah. So okay. I'll just define what accretion is because it's a word that I use so much but a lot of people don't even know what I'm talking about when I say I do black hole accretion. It's sort of what I throw out when it's like, what do you do? Oh, black hole accretion. Just walk away.
Oh, totally. Yeah, that makes sense.
But accretion it's the process by which the black hole gains mass. So in other words, like it eats gas that's falling inwards, and that's just called accretion. And so usually this happens, like, I don't know if is that image in the background, is that visible to the audience?
No, it's just what they can see now. Just kind of looks cool. You can kind of see it if you look down by Sean's name. There's a black hole here, and the rest is the. Event Horizon or something.
Yeah, it's like an artist depiction.
Yeah.
They're usually way better than anything that we can create from our simulations, just because we don't have any a lot of us don't have very many artistic qualities.
Yeah.
But in a lot of these images, you see like this like disky thing that's spiraling around and going inwards. And so that's generally how the gas falls in. It falls in these spiral patterns. Like it's literally just like water going down the drain in the toilet or whatever, how it spirals in. It's the same exact thing where the stuff coming in is like sort of rotating in a way, and then it just spirals inwards towards the black hole. And they call that an accretion disk.
Okay.
So the broad field that I work in is called accretion disk theory.
Accretion disk theory. Okay. This blew my mind when I was in grade school, and they were talking about gravity and space. And yeah, we always think of, or we used to think of gravity as like pulling, but it's really like a space pushing. And then I don't know if they dropped this or if I saw a video, but there's like a cloth or like a trampoline, and you put like a lead ball in the middle, and then you roll some balls around it, and they're like, look, it's bending space and time. And that's kind of like what Einstein discovered and helped us understand. What is it like? It's space bending in on itself or something?
So that's what's called general relativity, the theory of general relativity. So Einstein had like, I think, what is it called? His miracle year. He was like 20 something, like young 20, early 20s. And he did these three things that deserved to win the Nobel Prize. He won the Nobel Prize for one of them.
Yeah.
It wasn't the general relativity. But so general relativity, yeah, that picture of the ball on the trampoline is how gravity works in this framework. It's seen not really as a force like this. Like this was what Newton's theory of gravity was sort of like you had this ball over here, and somehow they magically communicated, and they knew that they should be attracted to each other, and so they would come closer and closer. But so a lot of people were they thought this was eerie. They called it spooky action at a distance, I think.
Right.
They used. So there's people always concerned about this, and it was like, what are they connected with some like mechanical rod that we can't see? What's going on? And so Einstein had this idea that it's not that they're magically communicating; it's that they're all sitting in this like trampoline, and that one ball is like weighs down the trampoline, so then the other ball that's not as massive will like fall around inwards or just otherwise be deflected by the curvature of the trampoline. And then the problem is that that's like a 1D picture.
Right.
What's happening is it's in 3D, so it's really impossible to visualize like the full like 3-dimensional trampoline, where it gets really confusing.
Yeah, I've tried to picture that before, and it really messes with me because I'm like, I'm pretty sharp. Maybe I can think of it, but it's like a trampoline and a trampoline and a trampoline.
Yeah,
like in every direction. Like it's so weird to think about, man. It really blows my mind. But so what I always thought, and obviously it's wrong, but was like black holes are like this big scary thing that's sucking things in, and it really just it gets anything in its way. And then prepping for our conversation, so pretty recently, they were saying no, it's not like extra strong.
Yeah.
If like a neutron star collapses into a black hole, it has like the same pull, right? It has like the same gravitational force. Is that right?
Yeah, as long as none of the mass escapes. So if for instance, the sun was a black hole right now, it just instantly became a black hole.
Yeah.
Other than the fact that we would no longer get light and we'd all die of a cold death.
Right.
We would orbit around in the same fashion. Nothing would change in terms of our orbit.
Okay.
What makes black holes unique is really how close you can get to them. Like if you're on the surface of the sun, you're going to have some intense gravity, but it's not going to be anything crazy. But now if you imagine if all that mass was contained in I think it's like a kilometer or something, if it was a black hole, then you could get incredibly close, and you would have these weird effects where like the gravity on your feet would be way stronger than the gravity on your head.
Yeah.
And so you would just get ripped apart by the intense gravity. And then also other cool things like time dilation, like time would move slower.
Yeah.
The intense gravity.
Okay. So that's so weird. But so the collapsing down, I think it's called like the Schwarzschild, radius or something like
Yeah,
that? Like,
force field radius is the event horizon radius for a non-spinning black hole.
oh, a non-spinning.
Yeah. The only difference when it's spinning is it gets reduced by like a factor of 2 or something. And
Okay.
it's just
But
the Schwarzschild is usually just called the Schwarzschild radius is the event horizon radius for non-spinning black hole. I almost
okay.
wanted to.
Well, you sent me a TED talk, and the lady was talking about. I should know her name. I was too busy trying to.
Andrea Ghez.
Yeah, there you go.
Won the Nobel Prize.
Can you say it one more time?
Andrea Ghez.
Okay. And she was talking about the Schwarzschild radius, and like if it's like if we compacted the Earth down to like a sugar cube, that would be it'd be a black hole then, because
Yeah.
it's got to be like compressed to this point.
Yeah.
And so the greater the mass, the less it's going to have to be compressed. Or like the greater the mass, the bigger the black hole.
Yes. Yeah.
Okay. But then someone else I was listening to was saying that like you couldn't do that. Like if you had some kind of machine, because I like philosophy, so we can make up machines whenever you had a black hole machine or whatever compressor, and you compressed the Earth down to a sugar cube, and like technically or theoretically it's a black hole. But someone was saying you can't do that because it wouldn't actually have enough mass, and not enough mass to actually be a black hole.
I don't. There's what they may be referring to is something called Hawking radiation.
Okay.
Which is there's a certain point if a black hole is too small, it can actually evaporate.
Yes. That's
okay. Yeah, it can evaporate by Hawking radiation, which is something that I don't completely understand myself.
Mm-hmm.
It's sort of something that you never really use in practice. It's almost like physics philosophy, though it really is physics. It's just like it's like Hawking being like, well, what would happen if this? Oh, wow.
That's why I bring it up, man. That's I love that. Just the woo crazy stuff out there.
There are plenty of like legit physicists who get sort of they get like pushed more and more towards that direction until everything they put out, you're like, what the heck are they doing? Like they don't even publish in like papers anymore. They just write it up on the internet.
Yeah, and they go on Joe Rogan, and and I learn it. Yeah.
Because when you get tenure, you can do anything. But yeah, Hawking radiation, I mean, it's a legit thing. It's like if you had, so in quantum mechanics, there's this thing where nothing is not really nothing.
I know. Yeah, it's so frustrating.
There's particles that can just pop into and out of existence, but it's
because nothingness is unstable, right?
Yeah, it's like there's particles can pop into and out of existence, but they have to pop up in pairs, like an electron and an anti-electron at the same time.
Okay.
Everything is conserved charge. There's no like all of a sudden there's no new positive charge or anything. The net charge is 0. The net everything is 0.
Yeah.
And so that happens like right outside the event horizon, and then one of the particles goes in and one of the particles goes out. And there's a way that instead of like net 0 gain, there's actually the black hole loses energy by it. Like one of the particles has negative energy and the other particle has positive energy.
Yeah.
And then the particle that has positive energy escapes. The one that has negative energy goes in. And so the black hole loses energy, which is essentially equivalent to mass in terms of the black hole. Okay. And then so the black hole shrinks a little bit. And for very small black holes, like what the Earth would be, this process is really efficient at causing the black hole to shrink.
Okay.
So it would just like evaporate into nothingness. But for larger black holes, it's completely negligible.
Okay.
Like any astrophysical black hole, the process for it to evaporate would take well beyond the length of the universe, the age of the universe.
Okay. So in researching this, I saw that there are at least 2 types of black holes. There's like the supermassive black hole, and then like the common, just run-of-the-mill black hole.
Stellar mass size black hole.
What's it called?
Stellar mass size.
Stellar mass size. Is that because they come from like neutron stars, or?
Well, they come from collapsing stars at the end of their life.
Okay.
So massive stars, generally when they die, they either turn into something like a neutron star or a black hole. And the only difference is the amount of mass in the core that survives. So if something doesn't have quite enough mass to become a black hole, it becomes a neutron star.
It's because like the mass or the force of the gravity can't overcome the energy of the neutrons or something?
Yeah. So there's this thing called like degeneracy pressure that keeps the neutron star from collapsing.
Mhm.
And this is so it's completely based on quantum mechanics. So this is kind of cool instance of where you think of quantum mechanics of being like these tiny things that you can barely observe,
Yeah.
but like a gigantic star that's entirely supported by quantum mechanical things. So it's like that's kind of like the craziest physics in real life that you experience. It's like neutron star.
Yeah,
What's
holy
going on
cow.
inside a neutron star?
It's like
But
the
what
nexus
happens?
of the tiny and the gigantic.
Yeah. And so it's like there's I don't know, in like chemistry you learn about electrons have energy levels.
Mhm.
And basically you get to a point where all the energy levels are filled up. And you can so you know how like there's this discrete energy levels. And to compress, you would have to go to like a higher energy, but
Oh,
there's
yeah.
no room for these particles to go in terms of like the quantum mechanical energy state. So this acts as a quote unquote pressure to keep it from collapsing.
Okay. And if that's if the mass that's like if the degeneration force isn't strong enough, then it resists that
If the
process of
degeneracy force is strong enough, then it
is
will fight against gravity and survive.
yeah. Well, okay, why would it be strong? Like can you give me two examples, like one where it's not strong enough and turns into a black hole, and then one where it is strong enough? What would make the one that's strong enough to resist becoming
It
a black hole?
doesn't have enough mass. So
It's
that's what happens is there's this maximum mass for a neutron star. We don't know exactly what it is. People are very actively trying to figure out. It's something around like 1.4 times the mass of the sun is like the maximum mass for
oh
a
yeah.
neutron star. So if there's more than that, then it will become a black hole.
Okay.
Because what happens is, so it's this kind of crazy thing in general relativity. So not only once you add mass, there's the pressure supporting gravity is an energy. So pressure is like an effective form of energy, and energy is an effective form of mass. So the more pressure you have, you're actually exerting more gravity.
Ah,
So eventually you just cross the limit where you increase the pressure, but that's also increasing the gravity. So it's this runaway process where it just collapses like in an instant almost.
yeah.
So
That's so interesting. Is
neutron
that a
stars get right up to the limit, and then if you just like poke it, it'll
yeah. That's so interesting. Oh, well, so that actually is why this dude I was listening to said that we couldn't become a black hole ourselves, is because that neutron star, uh, what you just talked about, we wouldn't have like enough mass or whatever.
yeah.
But I don't know. I think it's probably talking past each other because one is more like theoretical.
Yeah.
The Schwarzschild
If
is
you
like
were to
that's
like forcibly compress the neutron star somehow, you could
yeah.
form a black hole that way.
Okay. So if we had our compressor machine that made
Yeah.
me into a black hole, you could do that with a neutron star too.
Yeah.
That was resisting. Okay.
Yeah.
So when a
Really,
star,
it depends on how this machine
it's
works.
a good machine.
I'm
Yeah,
no engineer.
yeah. when uh when a star explodes or collapses, it does like kind of both, doesn't it? Like explode and then
Yes. So the core collapses, the outside part explodes.
why
And
why
there's
does that happen?
so there's so the basic picture is these are called core collapse supernovae.
Okay.
Supernovae is the explosion, and the core collapse is the black hole collapsing. Then what happens is like a star, a star starts out, it's like the sun right now. It's burning hydrogen in the center. So by burning, I mean the hydrogen atoms at the center of the sun are fusing. It's so dense and so hot that the like there's a helium atom or a hydrogen atom and a hydrogen atom. They get pushed together really strongly until poof, they become a helium atom.
And that's fusion as
Yeah,
opposed to fission, which is separating an atom
right.
or splitting
That's
or
what
whatever.
happens in a nuclear reactor.
Yeah. Okay.
And fusion is what like cold fusion is like the secret to infinite energy on Earth, basically.
Yeah,
But
clean and all that. Yeah.
figure out how to do. But so this is hot fusion in the sun. It's like ridiculously hot. So the particles are able to penetrate there. So the particles don't want to combine, but the heat makes them move really fast. They break through their barriers and they combine.
Okay.
So they form a helium atom or helium nucleus, and this process through which they combine releases extra energy, and that is what powers the star, causes all this radiation to hit us, and that's what keeps it from collapsing, is this process. So it keeps doing this over and over again for a long time until it runs out of hydrogen, because you only have a certain number of hydrogen atoms or hydrogen nuclei in the star.
Oh, okay. I didn't know that was a thing. So, oh wait, real quick. Okay. Does that depend on the size of the star, or could our sun have more hydrogen than a star way bigger than it? Is it just kind of a luck of the draw?
It definitely depends on the size of the star. I'm not a stellar expert, but I believe the more massive the star is, the faster it burns.
Oh, okay.
And the lower mass the star is, the slower it burns. But don't quote me completely on that. The funny thing is, at Santa Barbara, I'm surrounded by a bunch of stellar experts. Like, they just do stars all day. And I go to these meetings, and I'm like, I don't really know what they're talking about.
That's so funny. Dang. And you're like the villain to them. You're like the anti-star guy. You're like where the stars go to die.
Yeah. I'm the stellar remnant. Yeah.
Yeah. Dang. Okay, so oh wait, again, another one. Sorry to ask you stellar stuff, and feel free to say you don't know, but the size of the star doesn't necessarily mean it's going to burn hotter, does it? Because like a neutron star, don't those burn hot? Or no? I have no idea.
They're not really burning anymore. They're sort of just a big lump of mass doing nothing.
Oh, weird.
So, but the burning temperature does definitely depend on the mass, but also determines how long it lasts.
Okay.
So you can classify stars. There's this crazy classification system that makes absolutely no sense. It's because it was astronomy. Everything in astronomy is like that, because it's a bunch of people like 150 years ago, like staring up into the sky. Well, that looks like a B. That looks like a G. And then so they write it on, classify into these things like, this is an A type, B type, C type. And then you figure out later that these types have no correlation with the actual physics. And it's just like random classifications that you have to then teach forever.
And you've just inherited them, so you're not changing them now.
Yeah, that's a lot of things in astronomy.
Wow.
And they're not very creative either. It's like type A, type B, type C, type 1, type 2, type 3.
Yeah.
And then you get type 1A, type 1B.
Oh,
so,
no.
That's the big leap.
Yeah.
But so the stars are classified like A, B, C, whatever. And these are just effectively, they correspond to the temperature of the outside of the star. So the temperature of the part of the star that we actually see, and that directly relates to the mass of the star.
Oh, okay. I didn't know that. That's interesting. Yeah. It makes sense. You know, it burns, to burn hotter, you need more fuel going on, but that's going to burn quicker because it's hotter.
Yeah. So, but what happens in most of these stars is then, so you burn all the hydrogen, you fuse all the hydrogen into helium, and then so you run out of fuel to keep the star supported, and the core will collapse a little bit until it becomes even hotter, and then it can fuse the helium atoms or the helium nuclei.
Whoa.
And so then the helium will pop together and form carbon or whatever, like their various forms of burning. And so then it keeps doing that until it runs out of helium, and so on and so on.
Oh, okay.
Keep doing that and keep collapsing. The core will collapse. A lot of the times the outer part will expand. It will become like this, like a red supergiant. If you ever heard like a red supergiant, that's helium burning, I believe.
Okay.
So that's in the helium burning state. So, but it's a giant because the radius outside expands, but inside the core has actually shrunk and is at a higher temperature.
That's so weird. So, okay. Why the core is collapsing because it's running out of hydrogen, so it's moving to helium then.
Yeah.
I'm sure there's probably is there a name for that when it's like that first collapse from hydrogen to helium?
Probably.
Yeah, some A type, some weird.
I don't know what you mean like the transition, you mean like what the star looks like during that transition? Well, the transition generally happens so fast in terms of the stellar life cycle that all you see is either hydrogen or helium burning. There's like,
I mean, like, there's got to be like, it's probably called something when it switches,
oh,
right?
I mean, it's called. You mean like each individual stage, or
Yeah, I mean, maybe it's not.
like red supergiant, blue
Oh,
supergiant.
that's just the name of it. It's like, oh,
Yeah,
the core's collapsed, it's switching, now it's a red
yeah. It
supergiant.
depends on what the mass of what it turns into.
Okay, that makes sense. So then eventually, the core stops burning. There's no more helium left. Is it gaining carbon when it's doing
Yeah, yeah,
does that affect the core at all?
yeah. Because eventually, then it will start fusing the carbon,
Oh, okay.
and so this process just keeps happening until you get to iron. So iron is like element. Oh, great. What element is iron? 32. Am I wrong?
Dude, that's a long time ago for me.
Nico. This one Indian guy once told me like the best way to memorize periodic table was to put it into a string and then memorize the string. But it's like a completely nonsensical word. It's like Heli Bebkinoff, Al Sips Clark. I don't know why it works. Like it actually works. It's really easy to memorize, but it like makes absolutely no sense.
Dang.
But yeah, I think it's like 30 or 32. I don't know. Anyway, everything fuses until it reaches iron, and so then you have an iron core.
And iron doesn't fuse. Like it's nothing hot enough to fuse that.
It could fuse, but it would not actually produce any energy. So that's where the limit between fusion being the source of energy versus fission. Everything above iron, to get energy out, what's the
fizz?
Fission? You fizz it.
Yeah.
Fission is the process by which you release energy. So that's how nuclear reactors work. They get these radioactive higher mass elements and they just bombard it with particles and it splits and there's energy.
So I know, like, just from people talking about fusion and fission, that fusion is much more desirable. It seems like it's colder, or you can do it at cold level. It's less like extreme. It's just really hard to do, and no one can do it or whatever. But it seems like for a star to move from fusion to fission, it's in trouble.
Well, it doesn't move to fission. That's the thing. It's like it's imagine like there's this like U curve, and you're moving down from the left. Like say the left is. I wish I could like draw on this, but like going to the left, going down from the left is going from hydrogen to iron. Eventually, you're releasing energy during this process. And on the left or on the right, you can do the same thing starting from some crazy heavy radioactive element, and you keep fizzing until you reach iron. So iron is the most stable element. So it doesn't really want to do either of these things. It just wants to stay at iron. Everything wants to be iron. That's essentially what the
interesting
is. And so you get to iron, and it says, "Okay, now I'm stuck. There's no process by which I can get energy." So then it just collapses completely.
Okay, so
unless it doesn't have enough mass, and it becomes a neutron star or a white dwarf or something.
Yeah, that's good. There's so many
things. A white dwarf is basically just like a smaller neutron star.
Well, why? I should probably know this. Why is it a neutron? Why is it called neutron stars?
Because that's a question that I should also know. I mean, it's because the electrons and protons at such a high pressure, the electrons and protons sort of combine together to make neutrons.
Oh,
yeah.
Dang. Okay, that's sweet.
And they release. That's the process by which. So that's imagine like, I can't fuse anymore. What do I do? Well, I can combine these protons and electrons. And that will release a little bit of energy. That's like the next stage, and then there are all these neutrons.
It's kind of like
isn't 100% neutrons. That's sort of a misconception,
right?
But it's a lot of neutrons.
That makes sense. It's like to me, I'm just thinking it's like when you're hungry and your body is just like eat itself, and it's like it's eating all the excess fat, and then it's starting to move onto your protein, and then it's going into like your organs and weird stuff. And is that like a good analogy?
Yeah. Okay. It's like you use everything that you can until you can't.
Yeah, and then you become a neutron star and you explode, just like it happens to us when we're hungry. Yeah.
Yeah, the explosion is not. So the process by which the star explodes is not extremely well understood. It's believed to be so in the process of, like, for instance, in the process of like combining the electrons and protons, there's these things released called neutrinos.
Yeah.
And these neutrinos, they're incredibly small. We don't know what exactly their mass is, but they're these small particles that are neutral. So neutrino, I think it's just like little neutral one is like the root of the word.
And we get blasted by these from the sun, right? Don't
Yeah,
they just go through us? They go through the earth.
They interact so weakly with everything that they just almost do nothing. They just travel extremely fast because they have very little mass, and they just whiz around. And there's various types. But the idea is that there's so much energy released by neutrinos in the process of collapsing because of all these reactions that are taking place, that these neutrinos, there's so many of them that they add energy into the surrounding gas outside of the core, enough to make it explode.
Whoa. Dang, dude. That's crazy because the neutrinos, it's like a little nothing ball.
Yeah,
and
but
like they're the ones doing it.
It's
Holy cow.
10 times the amount of energy that is in a supernova explosion is released in neutrinos.
Dang.
It's just like this incredible amount of energy.
Do those get blasted out into the universe too?
Yeah. So we observe, there was a supernova that we observed via neutrinos.
Recently, or?
Yeah, I forget what the name of it is. But you can see the neutrino signal before you even see the
because they're so fast.
Yeah.
Yeah, because they're tiny and they travel. That's crazy. When I first learned about neutrinos, it like really messed with my view of myself. I really hated it, and I didn't want to think about it because I just felt like I was this big like chain link fence or whatever. That things are just passing through me. I'm like, no, I'm a solid, man. Dang it, I don't like neutrinos. But as I heard people talk about them more, I came to like them a little bit more. Yeah.
Well, I mean, you can like wrap your body around a Wi-Fi router, and people still get internet. So
I don't.
You all the time.
Yeah, it's just so weird when you go like subatomic with stuff. And it's cool. This is why what you were saying earlier about like neutron stars and stuff, the subatomic level, I'm forgetting now, quantum, and like the huge massive scale. It's so interesting that you're dealing with all this stuff. Like neutrinos are tiny, but then you're talking about this giant thing that's sucking in and accreting or engaged in accretion, this huge black hole. It's so crazy to think about like that exists in our universe.
Yeah.
The same universe where we have cars and dogs.
Yeah.
There's this thing it has a mass, but it doesn't have any like point. It's like one point in space.
Yeah.
Or it's like a eternally, like not eternally, but like it's reaching the point of no pointness or something.
Yeah, sort of.
It's like, isn't it like still shrink? Like if you jumped in it, this was crazy too. So I was researching this. If I went in like head first, I would be like elongated to like thinner than a hair, and I'd be like spaghettified.
Spaghettification.
Like, and I could not believe that was a real term, spaghettification. I heard Sean Carroll say that on Joe Rogan like a couple years back, and I thought he was making a joke. He's like, "This is a technical term, spaghettification," and they both laughed, and I was like, "Oh, that's funny." And then I hear actual other PhDs talking about spaghettification. You're like turning into a piece thinner than a piece of spaghetti.
I think there was an era. There was like a shift in like the 20s or something when people started trying to have fun with naming things.
Yeah,
like quarks. Like the name quark came from Finnegan's Wake, in written by James Joyce.
Okay.
And like they name them like the top down truth beauty quark, like and like things like spaghettification.
Yeah. They're just having fun because it's at the limits of our understanding. Yeah. It's bonkers.
They're like, we don't have to just use like Latin roots and stuff. We can do whatever we want.
I like it. It's like, yeah, what would a kid call that if you told a kid, "Hey, spaghettified"? Yeah, let's do that. I love it. So I wanted to talk about like supermassive black holes, because that's apparently something different. And people say that they're at the center of every galaxy.
Yes.
Is the supermassive black hole the thing that's making the galaxy look all cool and twisty?
No.
Oh, dang it.
So that is correlation, not causation.
Okay.
The reason it's at the center is the same reason that we're all orbiting the center.
Because of the trampoline.
There's all this dark matter.
Oh, I was going to ask you about dark matter,
Yeah.
dude.
So I can tell you. So the funny thing about dark matter is that we know everything about it except what it is.
Yeah.
We know where it is. We know what it does, but we have no clue what it actually is.
So some people, I'm here in Illinois, and we have the Fermilab, and they have switched from using their collider, because there's a bigger one, to they want to be like the number one people in dark matter. And I got a tour a couple years back, and they were talking about dark matter, and I talked about it on Facebook, and then some dude was like, "Yeah, I guess if you believe in dark matter." And I was like, "Well, I have no reason not to. I listen to them." And then people were saying how it's like phlogiston, or like every now and then, you don't have an explanation for something and you name it. Like in Thor, in the second Thor movie, a terrible movie, the red stuff was called ether. Ether. Like that used to be a thing, and now we realize there's nothing called ether or whatever. So like, how do we know about dark matter? Like, are you sure? Like, you're a dark matter guy. You're like, yes, there's dark matter.
I don't study dark matter at all.
But like, you believe in it.
Interest in it, but it's very clear that there's something dark that we can't see with light that is having gravitational influence. So if you take that, that's essentially the definition of dark matter. Like, the definition is so vague that you can't say it's not real.
Okay.
It's like, it's not like saying, oh, there's these like crazy quark things that just go around and whiz around and they have gravity but not do all these things. Like, we have a bunch of theories that sound crazy, like axions and WIMPs. So that's another instance of naming. So that's weakly interacting massive particles, WIMPs. It's like an in-joke.
Okay. That's a pretty good name. I like that one.
But those are two different things, really. It's like the presence of dark matter and what actually composes dark matter.
Okay.
And most of the dark matter theorists, like, this is kind of my cynical view, is every time I see one of the talks about what the particle is that makes up dark matter, it's like they propose a certain type of particle, and then they observe something and say, oh, it's not that type of particle. Oh, wait, I can tweak my model by like this one parameter, and now test. And then they're like, okay, fine, we'll test again. And then they test it. Nope, it wasn't that either. Like, wait, I can tweak it again. And then we'll test. And then the observer's like, really, we have to test again for this stupid model? Give it a rest. But one of them has to be right. There's just so many different models that it's ridiculous.
Okay.
It's really hard to constrain. But I think it's definitive that unless we have no understanding of gravity whatsoever, which is completely unlikely, then there's this large mass of matter that is not interacting with anything else electromagnetically, or it's not creating light.
And I think I've heard that there's supposedly more dark matter than non-dark matter in the universe.
Yes.
That's crazy. Is there like...
So, like, what's holding the galaxy, just to get back to the galaxy, like, what's holding the galaxy together, what's causing it to spiral around? There's this thing called a halo of dark matter. That's just this diffuse spread of matter that we can't see, that otherwise the rotation of the galaxy and everything, or all the stars, wouldn't make any sense. So you just know it's there because we know how stars orbit mass. Like, it's Newtonian physics.
Okay.
You don't even need like general relativity to do this. And you just see like stars orbiting. You're like, what are they orbiting? And they have a certain profile. Like, there's a star at a certain radius that's rotating at a certain speed. You go to a smaller radius, it's rotating at a different speed. And that profile tells you also not just how much mass is in the center, but how it's distributed.
Yeah.
It turns out it's not just like this massive amount of stuff in the center, which you could say, oh, it's just this gigantic black hole, but it's like this diffuse amount of gas. So for instance, the black hole at the center is 1,000,000 times the mass of the sun, but that amount of gravity is like completely negligible to us at the distance we are.
Right.
We're like 8 kiloparsecs away, where parsec is a really long unit that I don't know how to describe it in other words. It's just really long.
I didn't know that was a real word until researching for this, because I knew that like Han Solo traveled something in like the Kessel Run in like 12 parsecs or whatever, but that was a real thing. Parsecs.
Yeah.
Love it.
Yeah, I don't know what the actual definition is. It's like 10 to the 18 centimeters, if that means anything.
All right. So
A lot of centimeters.
so
Rulers.
well, dude, I guess since we don't know a lot about dark matter, I was gonna ask if like the supermassive black hole can suck in dark matter, but do we even have any
Yeah,
clue on that?
it should, because it's
Okay.
gravity.
So dark matter behaves like other matter, just not
In terms of
electromagnetically.
gravity.
What was that?
In terms of gravity.
Yeah. Yeah.
So like it could pass right through us.
Okay.
Because like gravity is like most of the forces that we experience on a day-to-day in our day-to-day life is not gravity, other than the thing that's keeping us connected to the ground.
Yeah.
Because like all the things that hurt, the things we hit, like those are like the reason they're solid like that is like the intermolecular forces that are pushing against things, like how we're, like you said, we're sort of like a chain link fence.
Yeah.
Like we're not really this solid thing. It's not like just solid on solid. It's like, so what exactly causes that? That's like electromagnetic forces between molecules and that. So if you had like this column of dark matter, you would be able to just pass right through it, unless it was so massive that it was causing you to gravitationally attract to it.
Oh yeah.
You have to have so much stuff for gravity to be important that it's like, if you just have a little bit of it, you're never going to know it's there.
Right, because like you have matter, and if I walk past you, I'm
Right.
not like feeling
Exactly.
Yeah. Can you explain? I don't know if this is in your area or not, but like there's 4 forces, right?
Yes.
Can you just do you know them off the top of your head, the 4 forces?
Yes.
Making you go back years here.
Okay, yeah. So there's the weak there. Well, the ones like if you're including gravity as a force, there's some. It's not obvious that it is a force.
Mm-hmm.
If you're thinking about it in terms of general relativity, gravity isn't really a force, because in the terms of like the trampoline is gravity. So the trampoline is that's just like geometry of the trampoline. It's not really a force between objects. But if you're trying to approach it from like the fundamental forces of the universe, from which particles exchange information to create forces, then people do consider it a force.
It's like an as-if force or something.
As a what force?
It's like an as-if force. Like you just kind of act. Yeah, just for talking, for communicating, it's as if it's a force.
Yeah, but also in terms of trying to unify all of physics, I think you have to think about it as a force.
Okay.
At least that's my understanding. So there's gravity or not, and then there's the electromagnetic force,
mm-hmm.
which is exchanged by light. So exchanged by photons, which are light particles. So that's what communicates that force.
There. So when like a magnet, when you have like magnetism, it's because
so like a magnet, and then also like a charged particle attracting another particle. They're the same force, really.
Cool. Okay.
And then you have the weak nuclear force and the strong nuclear force. So the strong nuclear force is what keeps nuclei together. Like if you have an atom, at the nucleus is like a proton, an electron, maybe a neutron. It's like what is causing the neutron to stay there? Like it's not charged. It has no charge. So why is it stuck there? Well, it's the strong nuclear force. So that, and even the electron and proton, or you can even have like proton, like 3 protons all stuck together. Like they should be repelling each other. But at a certain radius, the strong nuclear force becomes strong. That's why it's called the strong nuclear force. It's because it overcomes all the other forces and it allows these nuclei to stay together, but it only acts over a very short distance.
Okay, you got to be really close for that strong force. What I guess, man, what is the strong force? Like why what is it? What's happening? Why are these particles being stuck together like that?
I think that's probably able to be explained better than I can.
Okay.
I want to say it's not super well understood, but it might be better understood than I would make it seem if I said something like that.
Yeah.
Like, cause I took a class in nuclear physics, like that's basically like a graduate level, but that was basically my experience with that. And it was very ad hoc. Like you sort of say, oh, the force behaves like this, kind of, not ad hoc, but phenomenological.
Sure.
So when you say something's phenomenological, you're basically just modeling our experience of it, not the fundamental what's going on.
Right.
So if you see, like if you saw project like a basketball that somebody threw in the air and you saw the trajectory and you just said, oh, well, I can predict just based on, like, you plot every point and then you just fit a curve to it and say, well, oh, this is how it behaves. This is how the basketball behaves. But you're not actually saying, oh, this is because of gravity and air resistance. Like the non-phenomenological approach would have been to, okay, well, I know the mass of the basketball, I know its radius, I know how the air will affect it, and I know gravity of the Earth. So I can, in principle, just calculate what it's going to do without ever seeing it. Phenomenological goes backwards. It says, oh, I see how the ball behaves. Well, can I predict what another ball would do?
That's good.
So that is what my understanding of what we do within strong nuclear force.
Okay.
But the fundamental understanding is that it's a certain type of particle that, so like photons exchange the electromagnetic force, the strong nuclear force also has a particle that it exchanges with other, like a proton and neutron and electron. They exchange this type of particle, but unlike a photon, which doesn't have any mass, so light doesn't have mass. Yeah. This force is exchanged by a particle with mass, which is why it only acts over a short distance.
Okay.
Because the photon has no mass, it goes out to infinity. It just goes forever.
Yeah.
The particle with mass, it's not able to travel as far, so it works over a short distance.
Okay.
The name of this particle is escaping me right now. It might be something obvious. It's some kind of boson, which is just a type of particle, but I cannot.
It's not a Higgs boson, is it?
No.
Okay, I just pulled that word up.
Don't ask me about Higgs boson. I don't really know what that
is. I don't know either. It's just stuck in my head.
Important.
You're crushing it, dude. This is good. What's the weak force?
The weak force has to do with like neutrinos.
Okay.
And I don't have a good understanding of the weak force. It like never comes up in what I do.
Yeah. The only reason it comes up for me is I listened to a ton of Eric Weinstein.
Yes.
And he was like, one day he was talking to Brett Weinstein, his brother, and was like, I don't get how people can follow Game of Thrones or this show or that show with these complex storylines, but they can't remember that there's four forces. And I was like, dang, man, I should remember that there's four forces. So if I ever talk with him, I'd be like, yeah, the four forces, dude, totally. So thanks for just recounting that for us and all the listeners there. If you guys can recount the four forces, then you will also impress Eric Weinstein, maybe.
Or if you can, in terms of complicated plot lines, if you can remember the entire plot of the Kingdom Hearts series, that is also incredibly impressive.
It's right up there with the forces. Well, so going back to the supermassive black holes, does anyone know like what they are, what caused them, how they become supermassive?
It's debated. Okay. Because the weird thing is that you have the stellar mass sized black holes, which are like 1 to like 10 maybe times the mass of the sun. The supermassive ones are like 1 million to 1 billion times the mass of the sun. But there's really none in between. You don't see intermediate mass black holes.
Wow.
Sort of strange. So that sort of rules out, or it causes, it's possible that we just don't see them because black holes are hard to find. If they're not in the center of the galaxy or doing something crazy, they're just out there and they're not interacting with anything. They could be everywhere because you don't see them. That's the definition. They're black.
Yeah.
But it's weird that you don't see anything in between, because if it was just smaller black holes eating stuff, getting larger over time, you would expect like a distribution between.
Exactly. Yeah. You'd see a range of them going up.
So the process by which supermassive black holes form might be just a bunch of gas collapsing. Like there's no star really.
Oh, I've heard that. Yeah.
Like imagine if you had, like I think this might be what is referred to as primordial black holes. Like imagine if you just had a big, just gas cloud in like even before stars were formed, and there's just all this gas.
Yeah.
And it was uniformly distributed. So there's no like preferential way for gravity to pull anything. But
Okay.
then suddenly something shifts and there's like a little bit over density in one spot. Then the gravity there is stronger than everywhere else. It's going to pull everything in a little bit. But then as things gets closer, gravity gets stronger and it collapses even more. So it's this unstable gas cloud configuration, which then collapses. And it depends on the mass of this cloud and how fast everything collapses. But in principle, I think this is my understanding. This is also sort of cosmology kind of stuff. That's not, I don't usually think about black hole formation that much.
Yeah.
More of like a black hole pragmatic or practical. Once the black hole's there, then I'll deal with it.
Yeah.
But you just imagine if you had so much gas, like a ridiculous amount of gas, it would never even go to the star stage. It would just, because that's also how stars would form. If you had a certain amount of gas that was like, you would form stars in various spots, and then that's star formation as it collapses. Because eventually it would be collapsing, but then it would start fusing, and then that would support gravity.
And then when it's fusing, it like catches fire, and then that's
And so you would then have like stars and planets and all this stuff. But if you imagine that the gas cloud is so big and it collapses so fast, then gravity just beats out everything. It never forms a star or planet. It just forms this gigantic black hole.
Okay, so I'm thinking like, I don't know why my mind works like this, but I'm thinking like you have a big piece of paper and you got marbles distributed all across them equally.
Yeah.
And if you like pull down one part of that, they're all going to roll down to that, and that's going to make this black hole. But then that's going to offset the rest of it. You know, if you had this really, really big piece, then other marbles are going to get off kilter and they're going to go form another one, and then they're and they're just forming everywhere because one formed.
Yes.
Okay.
Exactly. That's a perfect analogy.
But why would they not turn into a star?
If like each localized patch had too much mass.
Okay, so it's because maybe the initial condition was just so much gas that it couldn't even, it just bypassed the star because it's just huge, heavy.
Yes.
And then when it's a black hole, like just again for everyone at home and for me trying to figure this out, it's so dense that nothing can escape it, not even light. So there's no way it's forming a star, because once you reach this point, it's like infinitely collapsing.
Yeah.
Is that right? Is that the right way to think about it?
Yeah.
Okay. Dang, man, this is sweet. Sorry I'm making you go at the limits and the extremities of your knowledge here, because you're focused on accretion, but you're really crushing it. So what made you want to go into accretion?
More happenstance than anything.
Okay.
I feel like that's the path of an academic, is like, it's sort of like a deterministic process. Like, I don't know if you've read War and Peace. Like
not like seriously. And
well, Tolstoy describes like the rise of Napoleon as something completely outside the control of Napoleon. Like a Napoleon was just going to show up based on history. Like all the previous events of history led up to a Napoleon forming. It's like Napoleon wasn't that great. He really didn't like Napoleon, I think. Napoleon was not nobody. He's just some guy that happened to be in the right place at the right time.
Right.
But I feel like that's a lot of what happens with academics. Like each individual person seems to have like a choice in what they work on, but what they work on tends to be influenced by who they were interested in working with, and then what the interesting problems were at the time when they started. Because I've basically come to the conclusion that most things in the field are interesting, and once you get into one of them, you find them so interesting that you don't want to stop.
Yeah.
And so you sort of just like, it's almost like this random, like at first it's random. You're just like, oh, well, that kind of seems interesting. And you start and then you're like, oh, this is really interesting. And then you get like sort of narrower and narrower.
Yeah.
That's my like philosophical view of that didn't answer the question at all.
Well, I think it's true. And it's also so weird because of where we're at in time, that you can be a specialist in this field and not know what your neighbor is working on down the hall, and not even like he'd have to explain it to you. Like not like he'd have to explain it to me, but you wouldn't know because you're so specialized in your area, because we've come such a far way from like Galileo, who like knew everything. I think it's just bonkers how much you can know and then miss out because you're like just 10 years deep in studying this one neutrino or whatever.
Yes. No, it's definitely very possible. And you would probably get a better explanation than I would, because they would assume a bunch of things that I know that I don't actually know.
Yeah. Okay.
Like the only thing that I can do better than you in that situation would probably be to pretend like I know what they're talking about.
Well, you'd have some concepts that I wouldn't. That would be really helpful.
I knew some words, some key words to say at the right moment, but I'm particularly bad about that, knowing like what's going on in other fields, because I tend to be a kind of person that just likes to focus on what I'm doing.
Yeah.
And just push, and in my own field, of course. Like I don't ignore what other people in my field are doing. But to actually answer the question of how I ended up here, I was interested in lots of theoretical stuff. Then in undergrad, I just thought the professor that was teaching mechanics which mechanics is like how stuff moves under like basic forces, like gravity and other things like that.
Mm-hmm.
And he was like the coolest guy ever, so I just wanted to work for him. And he was working on supernova remnants, so the stuff left over from when stars explode, which wasn't black holes, but that was just what I was like, okay, I'm working on this. Then I went to grad school, and Berkeley, I loved Berkeley. I loved the area, and I was like, I want to live in this area. And the guy that I would potentially be working with seemed really cool. And so I made the decision based on those like sort of feelings. And I went there. Then I started working with this guy. He was like, so his name is Elliot Quadert. And then he had me start on some like project with stars and magnetic fields for a couple months. And then out of nowhere, he's like, actually, I'm a part of this collaboration that I haven't been contributing that much to, but it's about like black holes and preparing for the Event Horizon Telescope. Would you be interested in that? I was like, yeah. And so then I started working on that, and that's where I am. I just kept going in that direction.
Wow. Just real quick, man. Do they have a Event Horizon Telescope?
Oh, yeah.
Whoa.
Yes. Oh, so did you not see this about a year ago in the news? The like picture of the black hole, that kind of thing?
Oh, yeah. Yeah. I remember totally. Okay, so that's what that was. Because I guess
basically my field, not the actual taking the telescope, but simulations that produce things that look like that.
That's what I thought it was. I thought it was like a rendering from a bunch of pictures or something. I remember someone explaining it and being like, that's not quite like a picture like we think. And I was all deflated, but maybe can you explain like what is that image? I almost put that as our background, but
yeah, it's not a picture in the sense that it doesn't work in the same way as a camera, but it is a picture in the sense that it's real data.
Okay.
It works by like they really don't take data in like, it's hard to describe this.
My frog just croaked back here, and I just want to make sure if anyone heard that, I didn't like pass gas or anything. That was my frog, so he's a bullfrog.
And he didn't like croak like metaphorically.
No, he's just. I think he hears my voice and thinks it's time he wants to do battle with me or something. But I'm still the big boss in this office for now. Yeah.
But yeah, so I mean, it's real data. It's a real picture, just not in the same way that you think of like just taking a picture where you have like basically you're just capturing where the light comes. Like it's a different process to capture the light and then make it like you have to put it through a process so that it looks like an image.
Okay.
In real space.
Okay. So that's sweet. You got that. And were you involved in that? Were you like around the periphery? Like what was the...
I was, so I'm not involved in that collaboration, though most of the people, it seems, in the field are. It's a very large collaboration. But that was like, it's one of those things where like every single introduction that I've written for every paper, every talk, you say, well, because of it's like one of the easy motivational kind of things. Well, in preparation for the Event Horizon Telescope, we're doing these simulations.
That's sweet.
A lot of motivation because it's like they already put in a bunch of money to this. So it's like, oh, well, you want to support that effort. But I'm not in the collaboration itself because the idea of being a big collaboration is really not appealing to me because it seems like endless meetings and politics.
Yeah.
Doesn't sound fun.
Yeah.
you can get a lot of the benefit from being outside, other than the actually knowing everything in advance. They did an amazing job of keeping all this stuff secret before they published.
Yeah. Well, this reminds me of another thing I want to ask you about. What I can't remember the name right now. I'm sure you'll know it. When I think it's in Argentina, when they picked up on gravity waves, I think, from two black holes bumping into each other.
Yeah, it wasn't just Argentina. It's like several places.
Okay. What's that called?
The Livingston International Gravitational Observatory, I think. LIGO.
LIGO. Okay. Yeah. LIGO. When did that
something in gravitational something.
When did that happen?
A little bit before then, maybe 2 years ago.
Okay. Yeah, I wanted to ask you because I remember that was pretty crazy. That's one that I was like, that's weird because like our reality like waved through and we didn't know because we're in this reality, and it's like someone like, made a wave in your fishbowl and you couldn't tell because you're in the fishbowl. But was that something that you were like pretty geeked up about, or was that just like, oh, that's pretty cool?
I thought it was cool. I mean, I expected it to happen for a while.
Oh, okay.
I was at a conference when the news came, and they just like ditched half of the day and said, "Okay, we're talking about this now."
Yeah.
Like, it was kind of fun because there were two people who were part of that collaboration who, like, I guess they knew. I don't know if they I guess they didn't know because they had scheduled other talks at the time.
Oh yeah.
That they just scrapped or they moved to a different day. But yeah, it's a lot of this stuff. It's hard to get excited when it's like a slow burn.
Yeah.
It's like, it's coming. Like, it starts off, you're like, oh wow, that would be really cool. And then it's like, yeah. And then you hear about it for like 4 years in a row. And you're like, yeah, okay, when are we going to see it? When are we going to see it? And then we see it. And but yeah, that's the only reason that I wasn't like, oh wow, that's amazing. Just because there's so much anticipation and build up and preparation.
Yeah.
That it would be like with the Event Horizon Telescope, it would have been amazing if we saw something that looked completely different, because what we saw looked exactly like what everybody kind of expected.
Yeah.
If we saw something crazy, that would have been really cool. But
if you saw another universe inside there,
I get excited about it, but I don't get that excited about like that kind of thing for some reason. I don't know why.
Okay.
I get more excited. Like, it's like, oh, that's cool.
Yeah.
But I don't know.
Well, how about have you seen Interstellar?
Yeah.
Did that like bother you, or did that get you? Was that exciting? Like, he went into a black hole and he
was to go home and work. Like, the whole thing about like humanity is not just a bunch of farmers like trying to survive. It's like there's a higher calling for humanity than just like be an animal that all it cares about is eating and living.
Yeah.
Yeah. Well, and a lot of physics was kind of accurate, except the crazy stuff at the end.
Yeah.
I really like that movie. A lot of people, what happens is that anybody who's an expert in something, if there's a movie about it, they all like to just crap on it.
Yes.
Like,
yeah.
Oh, yeah, wow, that was like, it's very easy to seem superior just by criticizing something.
Dude.
If you're criticizing something, you instantly feel like you're superior to it.
Yeah.
Easy, like even what I was just saying with like not being excited about the results. It's like, well, like, it was one of the most amazing things that we've done as a human race. And I'm here like, oh yeah, it wasn't anything special. It's like, oh yeah, because I work there, I know this stuff.
Yeah,
it makes you feel better about yourself, and makes other people feel like you know something just by criticizing it.
That's so true, man. I did a research, or I did a reading class on like theology and the philosophy of mind. So I was just deep into philosophy of mind stuff, and I watched Ex Machina, and I was like, well, they didn't technically get this right and that right, and then I realized exactly what you said, and where it's like, well, for one, I'm not even an expert in this, so I shouldn't be all like patting myself on the back. Two, it's a movie, and so they have to, and three, they did a really good job of looking into all this different stuff and explaining it in a way that, like, on the popular level could still be interesting. I was just like totally wrecked, being like, what an idiot. Why was I just going off? I wasn't talking to anyone. It was just me by myself watching the movie. But the higher power thing is interesting, man, because so for our audience, they don't know anything, but you're a Christian, right?
Yes.
So you're a Christian studying this stuff. Do you ever just ponder on like what is God doing with black holes? Like, why would God make a black hole or any, like, did he have to do this? Is this like he was, or was this like a beauty thing where he's like, I'm gonna put a black hole in the middle of this and I'm gonna let them discover that? Or is it like, no, if I want to make the universe I want to make, I need to have black holes and dark matter? It's total speculation.
Yeah.
But
I can't say I think about this too much. I usually think about theology and science in two different parts of my brain. Not
yeah,
not that they don't communicate,
right.
but just in general, my science thinking is never big picture.
Hmm.
On a day-to-day basis, it's like, oh crap, I left a semicolon out of this line of the code. Like,
Yeah.
that's the majority of the thinking in that respect.
Well, and you just completed your PhD last year too, so you were like super coming off of intense, like intricate into in-depth specifics.
Yes.
So that just for our listeners too, like I've had another guy who's working on his PhD in philosophy, epistemology, and he's so deep into the literature concerning what he's writing about that it's even hard for him to recall some like metaphysics kind of stuff, because it's like, dude, I'm not studying that right now. I spent 4 years researching this. Yeah.
I mean, it's even like I'm staying with my parents right now.
Mm.
And sometimes it's like they're talking, they're trying to, maybe not necessarily trying to get my attention, but they're trying to have like a casual conversation. And I'm just sitting there like walking, staring at the wall, like, yeah. Because I'm thinking about like how to debug my code and what's going to happen and what needs to happen. Your brain you have to be like hyper focused, otherwise you won't make it very far.
Yeah, that makes sense, man. I'm not that far yet. I'm just working on a couple master's degrees here, but I'm working on my master's thesis. And if something comes to me and I'm like, oh, that's a sentence I need, and it's going to really be a good transition, then I have to go run to my journal and write it down, because I'm like, I'm not losing this. I spent too long working on this, and it's like, dude, I'm so sorry. Hold on, give me 1 second. I got to write this down.
Yeah, but in terms of black holes and their theological importance, I would say I see it as like for some reason the church in like whenever that was, like Galilean times, got like really wedded to the idea that we're the center of the universe, the center of everything.
Right.
But like I feel like that wasn't even theologically sound kind of reasoning. It's
no, it was just a
never about us.
Right.
And it's clear there's a lot of passages where it's just talking about like how great the heavens are and like all the things that God created, showing how magnificent they are. And it's like, what are you, oh man? Like Job, like he spent the last couple of chapters being like, I did this and I did this and I did this. Do you know about this? Do you know about this? And Job's like, oh
yeah,
sorry.
I love it. It's my favorite part of the Bible.
I feel like that's like, I feel that paragraph, those couple chapters are like, that's what science is to us. Like that science is an alternative way of doing the same thing. Like, well, did you know about, oh, you guys are so smart, huh? Well, what about black holes? And what about neutron stars? And what about gamma ray bursts? And hey, guess what? Now there's fast radio bursts and you don't even know what they are yet. Huh. It's like the universe is so massive and there's so much cool stuff there that it's like, well, if the greater the complexity and beauty of creation, the greater you would infer the complexity and beauty of the creator. That's what I guess.
Dude, I love that. I love that you put it. I think you just opened up a can of worms about like simplicity, and that's a whole doctrine in theology, and some people are like, yeah no. but that's all right. The listeners at home can freak out about that. Well, the point that you made about it's like,
what is it like?
Well, whether God is composed of parts, does he have properties? And if he does have properties, you have this like bootstrapping, like either these properties exist outside of God and he's dependent on them, but God's not dependent on anything, or they're somehow like an ad hoc, like, well, no, they just belong to him. So I've on the podcast I've been having people on to talk about it, but because Richard Dawkins would say like, well, if this universe is so complex, then its designer must be way more complex. And it's not a good theory in science to posit something more complex as an explanation. And so then people are like, that's exactly why we need simplicity. And it's like, well, all right, dude, the principle of parsimony doesn't need to be brought in every second on everything when you don't have an explanation. there's an explanation over here, whether it's simplicity, a God of simplicity, or a God of parts. That's a better explanation in this scenario. And sorry to go on a
Didn't
thing
even
here.
make a theological statement when I said that.
I know.
Like,
I
God is
was trying to preempt
I
that.
think that he has the power to make something so complex,
Yes.
and the mind to make something. Like,
Yes.
his mind is so much higher and greater than anything we can imagine.
Dude, that is awesome. And I think what you were saying with Job, where it's like, it's just an extended, science is an extended paragraph. It's another one of those statements that God was saying, do you know
Yeah.
this? And I love that because it resonates. One of my professors, D.A. Carson, did that in class last semester. And he was like, he just extended that himself. And he's like, well, Job, he's like, today it'd be different. Today it'd be like, well, Job, is the electron a particle or is it a wave? Why don't you tell me? Because
Yeah.
Job, does it collapse? Did you collapse the wave function by observing it? You tell me if you know so much, Job. And it was just like, yes, dude, that's awesome, man. I love that.
I love it that he never actually answered. He never answered really what Job's question was. He was just like, awed him so much. He's like, you're asking the wrong question.
Yeah. Yeah.
You just answer the question you should have asked.
Yeah. Oh, dude, that's so cool, man. I'm all stoked on that. Just I don't know if I'm kind of scared to bring this up, but so you're not a stellar dude, but does the two-way speed of light like mess with your understanding of creation? Like,
what do you mean the two-way?
well, I guess like we don't know the one-way speed of light or whatever, right? Because we can only observe the two-way speed of light.
I actually am not. I have no idea what you're talking about.
Oh, okay. So maybe it's something that I've heard more in apologetic circles, but like in order to study or in order to know the speed of light, you have to know its two-way speed, like how long it takes to go to like a mirror and come back. Because every other way, if you used like a clock, because of Einstein, right? You take two clocks together, but then you move them. Now they're out of sync, and so in order to combat that out of syncness, whatever, you need like you have to presuppose the speed of light. But that's what you're trying to search for, anyways. And so I'm not doing a great job here of explaining it, but other astrophysicists or whatever.
What you're saying. I haven't thought about this at all, and I haven't really heard it discussed. So everything I say is going to be out of complete ignorance. But I think it's true that the fact that the speed of light is constant is a postulate of the theory of relativity, which then leads to everything else, which then seems to describe reality very well. So I imagine it being impossible to remove that postulate, because if you could, then it wouldn't be a postulate.
Yeah.
Because so we have a postulate in a theory. If in retrospect you say, actually, this theory comes out of only two postulates instead of three, you would have removed them. So I can imagine it being impossible to actually prove that statement.
Prove the one-way speed of light?
Yeah, something like that.
That's what people have said. And it comes up in Christian circles because they say, if you're a young Earth creationist or if you're an old Earth creationist and you're debating each other on how old is the Earth, because it seems theologically like it's this old, but it seems scientifically like it's this old. And so what do we do with this? Well, what about ancient starlight? So it takes this star is over here, and it would take this many years for it to travel to us. But we see the star right now. So the universe must be at least this old, because that's how far speed of light, how long speed of light takes to get to us. So this many years, because we see the star. And then someone comes up and says, yeah, but we don't know the one-way speed of light. We only know the two-way. And so maybe the one-way speed of light, or the first path getting there, if you're measuring it, takes this long, but then maybe the return is instantaneous. And it's like, well, how does that work? I don't know how that works at all. What do you mean instant? Why don't you just divide it by two? Take the two-way speed of light, divide it by two, half and half. That makes sense. And then, I mean, these guys are like physicists or whatever. And like, well, things are weird. The world's weird. So you can postulate that it's, 1.5 there and a half back, or it's 1 there and 0 back. And I don't actually know. I'm hoping to have a dude on to talk about this, but the world is super weird, man. The speed of light stuff is bonkers. But I was just asking that because I was wondering, for you personally as a Christian, how your work on the universe impacts your view of the creator and like how old the earth is and stuff like that.
I generally, in terms of like how old the earth is and whether the days are like 7 actual days or 7 periods of time, the yom thing.
Yeah.
Yom.
Yom or yom.
I feel like it's very clear that Genesis was not written as a science textbook.
Mm-hmm.
And that's kind of not an important question in terms of everything else. And I'm it's just one of those things like free will versus determinism that I'm perfectly happy to just say I am not going to be able to make any kind of conclusion on this, other than that I know that I have the faith that science, that God would not deceive us, in the sense that if science is really showing one thing pretty definitively, and any apparent contradiction with there's never going to be a contradiction between scripture and science, as long as we interpret scripture and science in the correct way.
Yeah.
Which is impossible for us to do completely accurately because we're mortal beings who have imperfect knowledge.
Yeah.
So if I tend to lean on the like days in Genesis as periods of time, and then whatever method we're using for estimating the age of the universe seems to be pretty reliable. And then just read the passages in Genesis, not necessarily through that lens, but just get what, like, because I feel like that's never emphasized as anything important in any book.
The days of Genesis, you're saying?
Yeah.
So
or how old the earth is.
Yeah, man, I actually kind of hate this conversation, this topic. I shouldn't have brought it up, but because it's people get very dogmatic on both sides.
Yeah.
And the science-minded folks are like, dude, you cannot believe this. You make us all look so stupid. And the conservative side in this debate, the young earth folks are like, dude, this matters for Jesus's genealogy, because in the beginning he created Adam and Eve, and Adam is traced all the way down to Jesus. So like, there's no gaps here. Where you're finding like enough room to fit in millions of years. And like, you can go to like an early church father, Augustine, if you want to call him an early church father. He's not that early, but he has a model of like old earth, young creation, where it's like God created the cosmos. The earth was formless and void. And what's that?
Tohu vabohu.
Yeah.
And then on that where he said tohu vabohu like 100 times.
That's great, man. And then he formed it in 6 literal days or whatever. And so that like complex model would have an old earth with like radioactive isotope kind of stuff, where you could look at some carbon dating and all that good stuff that would give you an old earth, but then a young creation which would accommodate the genealogy of Christ from Adam. And so, well, then you got some discrepancies with the Darwinist folks who were talking about, there's got to be like 10,000 humans in order for us to have the genetic variability that we have today. And so it's a whole mess, dude. And I'm pretty like not dogmatic on it. Like you said, I'm closer to you on that. And a lot of my friends, a lot of people listening are going to be upset both ways, which is fine. That's good. I like making people upset. I think there's other things that are more important for me to focus on, but I'm really glad that the other people are debating on this stuff, because I'll just go read your books. It'll be great.
Yeah, I mean, I think I take a hard non-dogmatic stance. That's my hard stance.
Yeah.
It doesn't really, I mean, it doesn't affect me in science, and it doesn't affect me in like my theology. So it's not an issue that I incredibly focus on.
Yeah.
Other than that, I'm using the exact same physical laws that they use to determine the age of the universe scientifically to do my research.
Yeah.
And those laws seem to be like, we use those for everything else, but why should we not use them also to estimate? Like, it's like, if you don't trust them to age the universe, why do you trust them to make your smartphone, or trust them to like use GPS or anything like that?
Yeah,
I feel like there has to be some level of consistency. It's like, you can throw out the science, but throw out all the science connected to the science that you're throwing out. Otherwise, you're just sort of deceiving yourself.
Yeah, picking and choosing, right? So I think what someone would say to that is like, yeah, God created with an appearance of age, not to deceive us, but because that's how you create things. You create them working. And so he didn't create Adam as a baby. And if you brought a doctor from today, he'd look at him and say, yeah, this guy looks like he's 19 years old, but surprise, doctor, he's 30 seconds. And so I'm just saying, I'm preempting someone in the comments, because I know it's coming, you guys. We know we thought through it. That's fine. Comment what you like, and give us some resources. That's cool too. Sean, man, this has been so great, dude. We've come really far from your specifics. I've made you go back a couple years and think through some hard stuff, and remember some things like the forces, and then we went all the way to Genesis. So we've covered a lot of stuff here, man.
Yes.
I'd love to have you back on. Would you be open to coming on another time?
Awesome. Yeah.
Yeah.
I mean, I can even keep going now, but if you need to go.
I have Old Testament class right now, actually. Okay. So remember, I'll tell her that you don't think Genesis is important for.
Yeah, he said throw out the book of Genesis. And start with Exodus.
It doesn't matter to him at all, man. Yeah. This is great.
How did Israelites get here? I don't know. It doesn't matter.
Doesn't matter. It doesn't matter. None of that matters. All right. So this has been Parker's Pensies. As always, all glory to God. This is going to have to do it for now, but Sean's going to come back on. We're going to talk more stuff, blow your mind, blow my mind. I'm pumped for it.